Hi, this video is about mechanisms of reactions, and we're going to concentrate on catalysts and intermediates. So first of all, we learned about the collision model, that in order for reactants to form products, the reactants must collide. But colliding is not enough. They have to collide with the right orientation. Remember, the reactants' bonds need to break and the products' bonds need to form, and they have to be in just the right orientation for this to happen. So there's also an energy requirement. There's something called the activation energy that we talked about in potential energy diagrams. That's that great big hill. And every reaction has an activation energy, and it's always positive. This is the minimum amount of energy that is required to start a reaction. So molecules have to collide. They have to collide in the right orientation and with enough energy to get over that activation barrier. There's only a very small fraction of molecules that collide that actually form products. At the very top of the hill, it's called the activated complex and is also called the transition state. And we talked about that when we learned about potential energy diagrams. But what's going on up there at the top of the hill? Well, that is actually where all the bonds are breaking and the new bonds are forming. So here is a potential energy diagram, and what we see here is we've got our transition state right here, so the top of the hill, and then the amount of energy it takes to get to the top of the hill, that is called the activation energy. Sorry about that. And then so the molecules are colliding, and they have to collide in the right orientation, and they have to have enough energy to get to the top of the hill, and that's where the bonds break and form. And if they get up there, then they're going to go on to products. So let's go ahead and talk about the temperature and the rate. Now, the temperature will generally increase the rate of a reaction. So the higher the temperature, the faster a reaction usually goes. And that kind of makes sense. So how does the temperature increase the rate? It's kind of three things that happen. More molecules now have enough energy to get over that activation barrier. A larger fraction of the molecules have the correct orientation now. And the number of collisions are more frequent because the temperature has gone up, the energy of the molecules are greater. So this is why temperature will increase how fast a reaction goes. Now, this is what I really want to concentrate on in this video, and that's called a reaction mechanism. The chemical equations that we write will show our reactants, so it shows us where we begin, and it shows us where we end in the products. But it doesn't tell us how we get from reactants to products. Most chemical reactions occur by several steps, and those steps are called elementary steps. And the mechanism is all of those elementary steps put together that lead to our final reaction. So let's go ahead here and let's look at this equation. Here it is up here. So nitrogen dioxide and carbon monoxide react to form nitrogen monoxide and carbon dioxide. Okay, that is our balanced equation. Here are elementary steps that have been proposed. The first step that they propose that happens is nitrogen dioxide collides with the nitrogen dioxide. It forms nitrogen trioxide and nitrogen monoxide. And then that nitrogen trioxide collides with carbon monoxide to give us nitrogen dioxide and carbon dioxide. Well, the question is this mechanism possible? What we do is we have to add these elementary steps up, and it needs to add up to the overall balanced equation. Now, when you add up balanced equations, what you do is if something appears on the reactant side, and then it appears on a product side, you cross them out. So look at how we've got a nitrogen dioxide here as a product, and here it is as a reactant. So we can cross one of them out, you know, 1 and 1. We also see we've got a nitrogen trioxide as a product, and here it is as a reactant. I don't think there's anything else that we can cross out. So now you just add them together. So all of the reactants from these two reactions that are left are nitrogen dioxide plus carbon monoxide yields nitrogen monoxide and carbon dioxide. And this is the same reaction as was proposed up there. So this mechanism is a possible one. And why can we say yes? Because when we add the equations together, it gives us the overall balanced equation that was given. Again, with these elementary steps, if there's something that's in the reactant side and it's on the product side in any of the elementary steps, you can cross it out. All right, now, let's go ahead and talk about something called molecularity. In each elementary step, the number of molecules that take part in the reaction determines what you call the molecularity. So if there's only one molecule, it's called unimolecular. 2, it's called bimolecular. And if there were 3, it would be termolecular. So here, this is a bimolecular step. And what we mean by that is 2 molecules. Let's see, I'm having trouble with my pen here today. Okay, this step here is bimolecular. And what we mean by that is 2 molecules have to collide in order to form products, bimolecular. So you have to collide with the right orientation with enough energy to get over the activated the activation energy barrier. And here this one is also bimolecular. Now, a termolecular would be 3 things all colliding and they all have enough energy and they all have the right orientation. And that's why it's rare, because it's rare for 3 things to collide all at once with enough energy with the right orientation. Okay, now in these reactions, in these mechanisms, we see things called intermediates. Intermediates are not present in our overall balanced equation. They're not there when we start. They're not there when we end. It's called an intermediate, and it doesn't appear in the overall balanced equation. It's made in one elementary step, and then it's consumed in another. So that's its definition, and its definition explains very clearly how to identify an intermediate. So let's have a look back at this reaction. So here is our elementary steps that were proposed, and we did add this up and we said, yes, this is a possible mechanism. And let's see, an intermediate, NO3, it appears in an elementary step and then it is used up. It does not. Oh my goodness, I'm having troubles today. It does not appear in the overall balanced equation. However, it is part of the mechanism. So NO3 here is what we call an intermediate. It is made and then it is consumed in another elementary step. So if we said, is there an intermediate in this reaction? The answer is yes, and it is NO3. Okay, let's look at this. This is an overall balanced equation, and here are the elementary steps that have been proposed. So let's see, is this mechanism a possible one? And if it is, let's name the intermediates. Okay, well, let's add these equations together, and then after adding them together, we will decide if it's a possible mechanism. All right, do we have anything that appears on the reactant side and then again on the product side that we could cross out? I only see one thing, dinitrogen dioxide. There it is. It's here as a product and here as a reactant, so we can cross that out. Now we can add, I don't see anything else we can cross out. And now let's add these together. Now, what all do we have on our reactant side in these 2 steps? NO and NO, let's just add those together and say 2 NOs plus an O2. These NOs don't cancel because they're not on opposite sides of the reaction. They're both reactants. Okay. Over on our product side, we have NO2 and NO2, so we add them together, and 2 NO2. This is a possible mechanism. It adds up to the overall balanced equation. Is there an intermediate? Is there something that's made in an earlier elementary step and then consumed later on? The answer is yes. And the N2O2 in this mechanism is our intermediate. It's made and then it's used up. Excuse me. Okay, here is another mechanism. Okay, so this would be the first step. Okay. So let's go ahead, and here is our first step, and here is our second step. Let's add this up for an overall reaction. They didn't give us an overall reaction. Okay, is there anything that's on the reactant side over here and also on the product side over here that we can cancel? It looks like fluorine can be canceled. This NO2, it's on the same side, so we can't cancel. They're both reactants. I think that's all we can do. All right, so this looks like our balanced equation. We've got two NO2s, one in this and that reaction, and we've got an F2, and it goes to 2 NO2F, and there we go. And I hope that's balanced, and it is. Is there any intermediate in this proposed mechanism? And the answer is yes, it's fluorine. Okay, let's try this one. This is our overall balanced equation. This is the proposed mechanism. All right, let's see what we got going on here. So here's the first step of our mechanism and the second. All right, do we see anything that appears as a reactant and then a product in another step that we can cross out in this mechanism? I see two I's here and two there, so I can cross these both out because there's a 2 there, and that is our overall balanced equation. Great. All right, what's the mechanism? This is a possible mechanism, and what is our intermediate? I is our intermediate. Okay, so hopefully you understand an intermediate doesn't show up in the overall balanced equation. It isn't present at the beginning of the reaction. It's not present at the end. It's made in an early step in the mechanism, and then it's consumed in a later step. So what is a catalyst? We said that they're substances, they speed up the reaction, they're not consumed, but in a mechanism they are there when the reaction starts, and it is regenerated when the reaction ends. And so it appears that it hasn't changed at all. But what it's actually done is it has another pathway for the mechanism that has lowered the activation energy. So here we have our potential energy diagram, and this dotted line is this reaction with a catalyst present. So it lowered the activation energy. And the way it does that is it proposes a different mechanism for the reaction. Notice what does change. The activation energy of both the forward and the reverse reaction is lowered. So in our forward reaction, the activation energy would have been 25 kilojoules, but after the addition of the catalyst, it's been lowered down to 10 kilojoules. So this new pathway that the catalyst has provided has kind of made the requirements lower for energy for the reactants to form products. And then what doesn't change with the catalyst is the heat or the energy of the reaction. With and without the catalyst, it started at the same energy and it ended at the same energy. All right, so let's look at this mechanism. This is hydrogen peroxide, and let's go ahead and add these two equations up and see what we come up with. Okay, so let's go ahead and add them up. All right, here's bromide, and here is a product. We got, let's see, water and water, but that's on the same side, so they're not going to cancel. Here we've got hypobromite as a product and a reactant, and that will cancel. And I think that pretty much does it. Okay, so let's add this up. It looks like we have 2 hydrogen peroxides, and then we're getting 2 waters and an oxygen. That's our decomposition reaction for hydrogen peroxide. Now let's ask the question, is there an intermediate in this? Is there something that's formed and then used up? Do you notice an intermediate? And there is an intermediate, and it's the hypobromite, the BrO-. It's made in step 1 and then used up. How about a catalyst? A catalyst speeds up a reaction, and the way it does it is by providing a new pathway, or a new mechanism, so that the activation energy has been lowered. It's present at the beginning of the reaction, but then it's regenerated at the end. This is our catalyst. Bromide is our catalyst. Do you see the difference between an intermediate and a catalyst? It's just a very subtle difference, but the catalyst is present at the beginning. It does take part in the reaction here, but it's then regenerated at the end. Okay, so let's have you go ahead, pause this, try this reaction, see what you come up with for the overall reaction, identify any intermediate, there can be more than one, and also identify any catalysts. Okay, so let's go ahead and add these together. See if you got this. Let's see, this chlorine is going to be crossed out, and the chlorine monoxide is crossed out. And I wind up with something that looks like O3, which is ozone, plus O yields O2, and there are 2 of them. Okay, so that's the overall reaction. An intermediate, looks like ClO is an intermediate. It's made and then used up. And the catalyst that speeds up this reaction is chlorine. Probably going to learn more about this reaction when you take environmental science. It's how ozone is depleted, and these chlorofluorocarbons in our environment, they act as a catalyst to speed up the decomposition of the ozone. All right, so here, were you able to identify an intermediate in a mechanism and identify a catalyst in a mechanism? And can you add up elementary steps to see if a proposed mechanism is valid for an overall reaction? If you can, you've got this.